cruising beneath the surface, an immense sea titan lurks in the abyss. Nearly 9 feet long, its tiny eyes poke out above massive jaws that span the length of a human forearm. As it hits the shallows, it props itself up at the water's edge and punts around, snapping up unsuspecting prey. It rests its body on large, weight-bearing fins, complete with shoulders, elbows, and even partial wrists. And it is these bizarre proto-limbs that will become the driving force behind one of the most spectacular events in evolutionary history. For this is Tiktaalik, a potential last common ancestor of amphibians, reptiles, birds, and mammals. The first step for vertebrates onto land. Tiktaalik was discovered in the Canadian Arctic in 2004 by Neil Shubin, Edwin Deichler, and their colleagues. The team had scoured maps to find rocks of the right age and type that were accessible at the Earth's surface, leading them eventually to find this remarkable fossil with an extraordinary blend of gills, scales, fins, and lungs, with a movable neck, sturdy ribcage, and crocodile-like head. Thought to have lived around 376 million years ago, Tiktaalik marks a crucial transition between aquatic and terrestrial forms of life, a missing link between fish and land animals. Or does it? For discoveries in Poland in 2010 of ancient footprints reignited the debate. These creatures possessed individual digits and exhibited a coordinated gait, suggesting they roamed the land up to 9 million years earlier than previously believed, long before the emergence of Tiktaalik and its fin-like structures. And so what does this mean? The more we investigate evolutionary junctures such as these, the more questions unfold. Does this mean that Tiktaalik was an evolutionary dead end? Or were its kin enduring pioneers that coexisted alongside their terrestrial descendants for millennia? Scientists eagerly await corroborative fossils, but the story shows that the journey is clearly far from a straight line. Evolution is complicated. And our evolutionary history is filled with a countless number of these mysterious junctures, where life branched and took 2 very different paths. Humanity's closest living kin are great apes, particularly chimpanzees and bonobos. Their likeness to us is eerily striking. You can see human-like features in their faces, their hands, their behavior. And so logically, scientists have thought that deep in our evolutionary past there exists a creature, the last common ancestor of all of us and all of them. But what did it look like? When did it exist? And again, is evolution quite that simple? British scientists have put together a list of 23 words that have remained mostly unchanged since the end of the last ice age, even across different language families. Worm, bark, mother, hand, fire, and 18 more. But unfortunately, these days languages are not quite so simple. This video is sponsored by Mondly, offering a fantastic 96% off lifetime access at mondly.app/HOH. Mondly is a language learning app with over 125 million users. It gives you access to 41 foreign languages from 33 native languages. 1,320 language combinations. In other words, if you speak Romanian and you want to learn English, French, or even Finnish, you can. It uses real conversations. With the help of a chatbot with speech recognition, Mondly can provide real-time feedback and help you improve your pronunciation quickly. There are daily lessons, weekly and monthly quizzes, and it's all very practical. Mondly focuses on usable lessons that will actually come in handy in your everyday life. So head over to mondly.app/HOH, where they have a summer sale, 96% discount for lifetime access to all languages. Says Owen, you can see, the brain of chimpanzee is always exceedingly small, with the hindmost horn of extremity shorn, and no hippocampus at all. It is 1861, and controversy is raging in scientific circles. Charles Darwin has long returned from a 5-year expedition on the HMS Beagle, his 1859 theory of natural selection positing that organisms adapted to their environments were more likely to survive and pass on their traits. And these revolutionary ideas have sparked a seismic shift in Victorian society. But Richard Owen, a formidable figure in the scientific establishment of the time, vehemently opposes Darwin's theory. For Owen, natural selection clashed directly with his devout Christian beliefs, which upheld the notion of each species being uniquely created and perfectly adapted. In the intellectual battleground of Victorian England, these conflicting viewpoints ignited a fierce debate that resonates through the annals of scientific history. In a series of groundbreaking scientific papers, Owen meticulously detailed what he perceived as defining traits of humanity's supreme form of brain. And among these characteristics was the unique presence of the hippocampus minor, a curved structure within the brain's lateral ventricles. Owen claimed that this feature underscored humanity's destined role as the unrivaled master of Earth and its creatures, suggesting that humans had transcended the animal kingdom. However, Thomas Henry Huxley, a staunch advocate of Darwinian evolution later known as Darwin's Bulldog, vigorously challenged Owen's assertions. Huxley embarked on a systematic exploration, dissecting primate brains in a quest to refute Owen's claims. His mission to demonstrate that the hippocampus minor was not exclusive to humans, but also present in ape brains, and in doing so, squash the popular attack on natural selection. Huxley aimed to unveil a crucial connection, a missing link that would bridge the perceived gap between humans and their closest primate relatives. In the unfolding drama of Victorian science, the clash between Owen and Huxley symbolized more than a scientific dispute. It encapsulated a profound philosophical debate about humanity's place in nature and the implications of evolutionary theory. The Great Hippocampus Question, as it was sensationalized by the media of its time, sparked a monumental public dispute that resonated far beyond scientific circles. Indeed, Darwin himself hailed Huxley's challenge against Richard Owen as a decisive blow, calling it a smasher. "Oh Lord, what a thorn you must be in the poor, dear man's side." The debate fundamentally reshaped perceptions of the boundary between humans and animals. It firmly situated humanity within the broader tree of life, illustrating how we evolved from a common ancestor shared with apes through the relentless process of natural selection. However, it also raised a not unreasonable challenge. Critics of Darwin's evolutionary theory posed a compelling question. If humans had indeed descended from ape ancestors, where were the transitional forms among present and past primate species? And so the quest for these elusive, missing links intensified as scientists raced to unearth fossils representing the last common ancestor between humans and other great apes. A pivotal piece of evidence to substantiate our evolutionary heritage. Darwin, drawing on anatomical similarities between humans and African apes like chimpanzees and bonobos, posited that these species were our closest living relatives. Given their presence in Africa, Darwin understandably hypothesized that early human ancestors, including the missing link, likely originated on the African continent, a radical idea for its time. Yet he found that his ideas about natural selection in relation to humans were being misapplied. The social Darwinism movement emerged that claimed that the struggle for existence in human society represents a form of survival of the fittest, providing a pseudo-scientific rationalization for social injustice and the hierarchy of classes in society. It is therefore perhaps unsurprising that when Darwin suggested the missing link should be found in Africa, he was met with strong resistance. Indeed, some countered that Asia would be a more civilized birthplace for humankind, emphasizing similarities between humans and Asian gibbons. And so, the search began. Where would the answer be found? Scientists didn't have to wait long for options to appear. In 1886, the first non-human hominin was recognized as a distinct species from a skull discovered in 1854 in Germany. The local newspaper had reported the find. In neighboring Neanderthal, a surprising discovery was made in recent days. The removal of the limestone rocks, which certainly is a dreadful deed from a picturesque point of view, revealed a cave which had been filled with mud clay over the centuries. While clearing away this clay, a human skeleton was found. Yet Neanderthal 1 was never considered a candidate for the missing link, as its bone structure was considered too different. Dutch anatomist Eugene Dubois, abandoning his academic career to search for the missing link, discovered a creature that looked human, yet not quite modern, along the banks of the Solo River on the tropical island of Java in Indonesia. He called the find Pithecanthropus erectus, meaning upright ape man, and this fossil came widely to be known as Java man. Some scientists dismissed the fossil as an ape and others as a modern human, but we now know that Java man likely lived between 700,000 and 1 million years ago and belonged to Homo erectus, a hominin species that is actually much more recent in our evolutionary timeline and much more human-like than ape-like. And then, 2 decades later, the quest for the missing link returned to Europe. Amateur archaeologist Charles Dawson reported that when excavating an ancient gravel pit near the site of Piltdown in East Sussex in England, he found a human skull with unusual characteristics. And so he claimed that whilst the skull itself was very much human-like, the jaw and teeth appeared to resemble a modern ape. Piltdown Man, as the specimen was henceforth nicknamed, was now the leading contender. That was, until it was exposed in 1953 as a fraud. Dawson had knowingly mispaired a modern human skull with an orangutan's lower jaw, misleading the scientific community on their quest. Unfortunately, this fraud substantially affected the course of early research on human evolution. It led scientists down a blind alley. Discoveries of Australopithecus fossils, such as the tongue child found by Raymond Dart during the 1920s in South Africa, were even initially ignored because of the support for Piltdown Man as the missing link. Luckily, nonetheless, Dart's discovery of ancestral humans in Africa marked the beginning of the acceptance that the missing link would be found in Africa, which was cemented by further fossil discoveries in the late 20th century and early 21st. And so the main question that now remained was how different hominin species emerged through the process of evolution. Darwin himself depicted evolution as a branching process in which ancestral species divide into 2 or more descendant species. But a long-standing tradition of organizing nature hierarchically, one that dated back to famous Greek philosophers like Plato, remained rampant within science. And thus, many interpreted human evolution as unfolding in a linear fashion, from simple to complex, primitive to modern. Of course, we now know that evolution does not march steadily towards humanity. Rather than a linear progression as some scientists once imagined, modern science recognizes evolution as a branching process, with scientists focusing on understanding its mosaic nature, where multiple hominin species may have coexisted and displayed a variety of traits. This understanding of evolution as an expansive family tree, rather than a single long branch, means that many hominin species we have discovered might not actually belong in our direct line of ancestry. Instead, they may represent side branches of humankind. And new discoveries constantly add to this intricate picture, involving a diverse array of ancestral species and transitional forms, with no straightforward chain of development from ape to human. But this does make it incredibly difficult to pinpoint the exact missing link between humans and chimpanzees, and work out how human and ape species diverged through deep time. Although that hasn't stopped scientists from trying to untangle the complex evolutionary relationships between humans and our primate cousins. Rather, a convoluted family tree makes the search for the last common ancestor, the missing link, an even more exciting challenge. Discoveries of fossil evidence become different pieces of the same puzzle. And as the puzzle builds, we are beginning to learn more and more about the moment our branch of the family tree split from all the rest. Twice as hot as our sun and 1,000,000 times brighter, Earendel sat in the sky undetected by scientists for decades. Discovered by the Hubble Space Telescope in 2022, Earendel is the earliest and most distant known star, at a co-moving distance of 28 billion light-years. The light recently detected from Earendel by the Hubble Space Telescope was emitted only 900 million years after the Big Bang. Earendel even has a small probability of being a population 3 star, meaning it contains almost no elements other than primordial hydrogen and helium. Such stars existed in the very early universe and would have started the production of chemical elements heavier than hydrogen, which are needed for the later formation of planets and life as we know it. However, until the discovery of Earendel, the existence of population 3 stars were only ever inferred from physical cosmology, from theory. Earendel could be the first population 3 star to be observed directly in the sky, showing that whilst it is incredibly difficult to find them, it is at least fairly straightforward to identify the first stars from their chemical makeup. Pinpointing the first hominins, however, remains a completely different ballgame. Indeed, is it even possible to identify the missing link? How would we know if we found it? What are we even looking for? In their quest to uncover the last common ancestor between humans and chimpanzees, scientists focus on a range of morphological, genetic, environmental, and behavioral traits that can offer clues. One of the critical morphological traits is the transition to bipedal locomotion. We can look for fossil evidence of this change in the pelvis, femur, and foot structure that suggest an adaptation to walking upright. The shape of the pelvis and the angle of the femur in relation to the knee are particularly telling. The structure of the skull and its size are also pivotal for revealing the evolution of the modern brain. Capacity and the shape of the skull helps determine when brain size and complexity reach that comparable to our own, whilst other features, such as the position of the foramen magnum, the hole in the skull where the spinal cord passes through, can also indicate whether a species was more likely to walk upright or on all fours. The use of tools is also a significant indicator of our advanced cognitive abilities. Intentionally flaked stones or modified bones indicate developed problem-solving skills and dexterity. Scientists can then compare these tools with those used by both modern chimpanzees and early humans to help identify the roots of human behavior. Scientists can also study the size, shape, and wear patterns of teeth to infer dietary habits and social behaviors, and understanding the environment in which the last common ancestor lived is also crucial. And finally, and perhaps most importantly, the discovery of the structure of DNA, the genetic code that controls all life on Earth, in 1953 revolutionized science and our ability to understand our evolutionary history. It enabled us for the first time to search for genetic markers and mutations that are shared between humans and other species. And this comparison of the human genome with that of other species showed conclusively that we are indeed the most closely related to chimpanzees and bonobos, just as Darwin had suggested. In fact, we are even more closely related than Darwin could ever have imagined, sharing nearly 99% of our DNA. Genetic data indicate that the human side of the primate family tree, known as the subgroup hominins, split from that of chimpanzees and other apes about 7 million years ago. And so for the first time, this gave us a rough time frame in which to search for the missing link. Yet determining what an organism should have looked like at the base of an evolutionary tree is extremely hard. But we do have some options. A handful of human-like fossils have been discovered in Africa that lived around or shortly after this time frame, and therefore have been argued to be potential contenders, or at least informative, about the last common ancestor, or LCA. In 2001, in the Jurab Desert of northern Chad, the remains of 6 individuals of a previously unknown species and genus were discovered, believed to date around 7 million years ago. They were called Sahelanthropus chidensis. A skull was among those remains and was nicknamed Tumai, a name from the local Daza language meaning hope of life, given to babies born just before the dry season. Tumai became a source of national pride in Chad. Michel Brunet announced the discovery to a televised audience before the Ministry of Foreign Affairs. The ancestor of humanity is Chadian. The cradle of humanity is in Chad. Tumai is your ancestor. Initial analysis of the Tumai skull suggested that Sahelanthropus stood upright and walked bipedally like modern humans today. The position of the foramen magnum especially, the hole in the skull that connects to the top of the spine, was directly underneath the skull, providing the support necessary to walk on 2 feet. That was until a graduate student at the University of Poitiers in France stumbled upon what was labelled as a box of animal bones but contained a hominin femur thought to belong to Sahelanthropus chidensis. The student took the bone to the head of the Department of Geosciences, who considered it to be inconsistent with bipedalism. This contradicted what the original team had stated in their initial descriptions of the species, using only the distorted skull of Tumai. And following some initial backlash, the description of the femur was published in 2020, concluding that Tumai was not bipedal. But that wasn't the end of the story, for in 2022, 3 hominin specimens, originally excluded from the analysis of Sahelanthropus, were analysed and included within the discussion. These latest reports suggesting that the material is consistent with bipedalism, but that clambering through trees was also probably still a key mode of locomotion. Scientists therefore asked whether they had found the missing link. Could it be Tumai? Another possible contender was Orrorin tuganensis, a genus first discovered from a tooth in the 1970s, but named in 2000 when further fossils were uncovered in central western Kenya. Orrorin means original man in Tugan, a language spoken by 200,000 people living in the Tugan Hills. The oldest fossils of Orrorin are thought to be around 6.1 million years old, and the youngest are around 5.7, and therefore had potential to be candidates for the missing link. Whilst we have no skull, the Orrorin fossils contain some unusually well-preserved thigh bones. The study of these has shown them to be intermediate between Miocene apes and Australopiths in shape, raising Orrorin as a clear contender for humanity's 6 million-year-old ancestor or close cousin. Indeed, further studies of the femora have shown solid evidence that Orrorin walked in an upright bipedal fashion, something that has been challenged far less than the nature of Sahelanthropus's bipedality. And so Orrorin tuganensis and Sahelanthropus chidensis offer tantalizing windows into ape evolution around the time of the missing link. One perhaps partially bipedal, the other fully so, they represent the period of this change, along with a multitude of hominoid populations that existed in the era of the missing link. One final and perhaps unlikely contender is Ardipithecus ramidus, one specimen of which is affectionately known as Ardi. The name Ardipithecus ramidus stems mostly from the Afar language, spoken in the Middle Awash River Valley of Ethiopia, where the fossils are found. Ardi in Afar means ground or floor, and Ramid means root. Therefore, the name literally means the root of human-ape ancestry. In 1992, a research team headed by Tim White of the University of California, Berkeley, discovered the first Ardi fossils. More fragments were recovered in 1994, amounting to 45% of the total skeleton, which were dated to between 4.35 and 4.45 million years old. Ardipithecus ramidus therefore existed much more recently than the most recent common ancestor of humans and chimpanzees, and thus cannot be fully representative of the last common ancestor, despite its fitting name. But even if Ardi is not on our direct line, it must have been closely related to the direct ancestor, and thus is probably similar in appearance and adaptation. It also offers interesting insights into how we evolved from the last common ancestor. For example, its less pronounced canine teeth have been used to infer aspects of early hominin social behavior. It's been suggested that the last common ancestor of hominins and African apes was characterized by relatively little aggression between males and between groups. This is markedly different from social patterns in common chimpanzees, among which aggression is typically high. Also, the canine teeth are less sexually dimorphic, suggesting increased pair bonding and increased investment from parents in the upbringing of their babies. These are characteristics that are thought to be specifically human, suggesting that RD may indeed be on our evolutionary line. 30 years ago, none of these species had been unearthed or identified, marking significant strides in substantiating the narrative of human evolution in Africa. Remarkably, the timelines of these discoveries align closely with the genetic predictions for the divergence between chimpanzees and modern humans. And so, can we confidently say that Tumai, Orrorin, or Ardi are the missing link? Unfortunately, no. Despite dating to around the right time of the genetic divergence between humans and chimpanzees, scientists generally do not see these fossils as the elusive missing link. Instead, they view Sahelanthropus chidensis, Orrorin tuganensis, and Ardipithecus ramidus as close relatives of the last common ancestor, or evolutionary side branches, dead ends that nonetheless illuminate the broader context of our lineage. Take Orrorin tuganensis, for example. This species displays a blend of ape-like and early human traits, including potential adaptations for bipedalism, a hallmark of hominins. Yet the incomplete fossil record leaves its precise place in our evolutionary tree shrouded in mystery. Orrorin tuganensis dates to around 6 million years ago, a timing that places it near the last common ancestor, but does not necessarily make it a direct ancestor. It could represent a lineage that branched off close to the divergence point, contributing to our understanding of early hominin evolution without being on the direct line to modern humans. Then there is Sahelanthropus chidensis. This species presents a fascinating mix of primitive and advanced features. While its small brain size is reminiscent of modern chimpanzees, its facial structure and dental morphology are more hominin-like. But the exact place of Sahelanthropus in our lineage is hotly debated. Some researchers argue it could lie on the direct path to humans, perhaps very close to the split between humans and chimpanzees, but many see it as an earlier branch that veered off and did not lead directly to modern humans. And finally, Ardipithecus ramidus stands out for its combination of bipedal and arboreal adaptations. With extensive and relatively well-preserved skeletal remains, the Ardi specimen offers a detailed glimpse into an early hominin that could resemble the last common ancestor. However, again, while Ardi shares many traits with later hominins, its exact relationship to our direct lineage remains unclear. Ardi lived approximately 4.4 million years ago, placing it broadly contemporaneous with other early hominins, which further complicates its placement within the evolutionary tree as a direct ancestor. And so while Orrorin tuganensis, Sahelanthropus chidensis, and Ardipithecus ramidus may not be our direct ancestors, they are invaluable in painting a richer, more detailed picture of our evolutionary journey. However, that is not the end. We've only heard half the tale. What about the chimpanzee side of the story? Unfortunately, again, primate fossils from this time period are even more rare than the hominin ones. Miocene primates, such as Proconsul, Dryopithecus, and Civipithecus, have been found in Africa, primarily in Egypt and in Asia, but none of these seem to be directly informative about our most recent primate ancestors, dating much earlier than the human-chimp divergence. The sparseness of the fossil record means that our current understanding of hominin evolution is based on a patchwork of evidence, a puzzle with missing pieces. But there is still a lingering question from anthropologists. Do we actually need the missing link to understand the connection between humans and our primate ancestors? And is it even a useful concept? for thinking about human evolution. A creature living between land and water wades through the shallows, searching for shellfish and mollusks within the reeds. It is not Tiktaalik, but something more recognizable, something more human, an aquatic ape. First proposed by German pathologist Max Westenhofer in 1942, the idea resurfaced through the work of English marine biologist Alistair Hardy in the 1960s. Hardy envisioned an ancient ape diverging from its terrestrial kin, driven by competition into coastal and marine realms. This bold hypothesis proposed that these aquatic pressures spurred adaptations in our ancestors, influencing modern human traits. Hardy drew parallels between human and marine mammals. He highlighted human behaviors such as front-facing copulation, rare amongst primates but common in cetaceans like whales and dolphins, as evidence of a historical aquatic phase. In Hardy's vision, this aquatic interlude reshaped our ancestors, imprinting them with distinctive features that endure in modern humans. And so, have we been looking for the missing link in all the wrong places? Anthropologists generally do not take the concept of an aquatic ape seriously, despite its popularity among the public. The aquatic ape hypothesis falls under the category of an umbrella hypothesis, attempting to explain a wide array of traits, many of which may not be adaptive, through a single evolutionary pressure. As well as this, of course, the notion of an aquatic phase in human evolution contradicts what we know from the fossil record of early hominins found in Africa. Species like Sahelanthropus tridensis, Ororhyntuganensis, and Ardipithecus ramidus lived in terrestrial landscapes, not coastal environments. During the Pliocene era in Africa, bodies of water were probably hazardous, inhabited by predators like hippos and crocodiles, which would have posed significant threats to early hominins. It's also very difficult to imagine how the specialist bipedal features of modern humans today would have evolved in an aquatic environment, where balance and weight transfer mechanisms are far less important than they are on land. Current evidence from the fossil record points to bipedalism evolving very early on. Indeed, Sahelanthropus, Ororhyntuganensis, and Ardi all show some signs of being bipedal. It's therefore argued by many to be the hallmark of being a hominin, with humans being unique among living primates in the way they move around. Bipedality therefore becomes a core component for understanding the deep ancestral connection between humans and the other great apes, and the evolutionary processes that caused divergence. African apes have lived in tropical rainforests for the last 30 million years, foraging for fruit, herbs, and leaves within trees. It is believed that the divergence between apes and hominins occurred under changing environmental conditions, when large areas of the landscape became increasingly dry as a result of climate change. A less wooded and more open environment required early hominins to develop strategies to cope with ever more sparsely distributed food and cover. Standing and walking on 2 feet would have enabled hominins to feed on different levels in these changing landscapes. Freeing up the hands and enabling access to new food resources, such as seeds from grasses or animal carcasses from predator kills, may also have acted as a form of positive feedback, resulting in further selection for features that facilitated bipedal locomotion, as well as scavenging and hunting behaviors. Bipedalism may also represent a heat and shade adaptation, reducing the surface area exposed to the sun in these increasingly open landscapes. Humans engage in striding, obligate bipedalism, where one leg moves in front of the other, requiring a unique and particular set of adaptations, such as our skull being placed directly on top of our spine, facilitating the support of a vertical trunk and efficient weight transfer through the legs. This was a feature already present in Sahelanthropus 6 to 8 million years ago. We've also lost many useful features of climbing, such as an opposable big toe, curved fingers and toes, and adaptations in the shoulder joint. Indeed, our loss of ability to move around in trees is almost as important as the acquisition of specialist bipedal adaptations, as it points to strong selective pressures for bipedal locomotion, exclusively on the ground. By comparison, chimpanzees spend very little time walking upright. When they do, it is usually postural, for example standing up to pick fruit in tall bushes rather than during actual locomotion. And so what does this mean then for locomotion behavior of the last common ancestor of chimps and humans? Some originally believed that the last common ancestor would have moved primarily swinging from the underside of one branch to another. This theory, however, has fallen out of fashion, primarily because proconsul, a Miocene primate, has limbs that would only support above-branch locomotion. This means that while proconsul could climb up branches, it would have to stay on top of them and probably could not move around by brachiation. Early speculation had thought that proconsul might be a transitory form between monkeys and great apes and hence an ancestor to humans. But genetic data has disputed this, showing that proconsul, existing about 21 to 17 million years ago, is just too old to be considered a candidate for the last common ancestor of humans and chimpanzees. Another theory is that the last common ancestor may have possessed arboreal bipedalism, a way of walking on flexible branches seen in orangutans, requiring knee and hip extensions that mirror humans running on springy tracks. Human bipedalism could therefore be seen as less of an innovation, but an exploitation of a movement behavior retained from the missing link. Others propose that humans have a knuckle-walking ancestor based on the features in the wrists of chimpanzees, gorillas, and critically, Lucy, Australopithecus afarensis. This theory favors a missing link like modern apes, but we have not yet seen a single Miocene ape that exhibits any anatomical features definitively relating to knuckle walking, nor do modern human hands show evidence of knuckle walking ancestry. And finally, some combine these theories to suggest that bipedalism developed through a succession of such phases, with full bipedalism like we use today only emerging with the genus Homo between 2 and 3 million years ago. And so does that mean that the evolution of bipedal locomotion was a slow, gradual, linear process? Not really. Sahelanthropus, Ororhyntugonensis and Ardi, as well as more recent hominin finds, suggests that actually there is much more taxonomic diversity in the fossil record than originally thought. Although the fossils are very fragmentary, it appears that each species has a mosaic of adaptations, with every fossil retaining a different combination of arboreal versus bipedal characteristics. Instead of suggesting a straightforward transition towards upright bipedalism seen in modern humans, these discoveries portray a complex diversity of movement behaviors, challenging the notion of a single linear evolutionary path, from tree swinging to two-legged walking. Bipedalism therefore may have arisen through several different evolutionary pathways. Indeed, some have argued that it's much more likely that the missing link was a generalized ape that could engage in a number of different traveling behaviors to suit different needs. Much like today's chimpanzees, the last common ancestor may have knuckle-walked, but also been very good at climbing and engaging in suspensory behaviors, as well as being occasionally bipedal. If this is the case, the current contenders from the African fossil record could be too human-like to actually be the missing link. And so while candidates like Sahelanthropus, Ororhyntugonensis and Ardi have all contributed valuable pieces to the puzzle of our evolutionary history, the quest for the elusive last common ancestor remains ongoing. But what else do we truly know about the life of the last common ancestor, beyond their movement? What glimpses can we glean of their cognitive ability and social worlds? Tool use is a fascinating starting point. Both modern chimpanzees and humans are skilled tool users, suggesting our ancestors possessed at least rudimentary tool-using skills. Archaeological finds of stone tools, dating back to over 3 million years ago, show signs of intentional flaking, indicating foresight and planning, and chimpanzees today use a variety of tools for activities like nutcracking, termite fishing, and hunting. The complexity and diversity of these tools suggest the last common ancestor might have had a similar knack for using objects to solve problems. Observing chimpanzee tool use has been argued to provide a living model to infer the behavior of the last common ancestor. and the ability to use specific tools for particular tasks and teach these skills to offspring implies cultural transmission and learning, hinting at the sophisticated behaviors that might have existed in the last common ancestor. And the heavy cognitive demands of tool use also likely influenced brain evolution. Leslie Aiello and Peter Wheeler's expensive tissue hypothesis proposes that the metabolic costs of a larger brain are offset by a reduction in gut size, facilitated by a higher quality diet that rudimentary tools help secure. A positive feedback loop between complex cognition afforded by increasingly bigger brains and innovations in tool use may explain why we have become the tool-using species we are today. And finally, the social structures of modern chimpanzees and humans may offer further clues about the last common ancestor. Chimpanzee communities exhibit intricate social behaviors, including cooperation, conflict resolution, and alliance formation, underpinned by cognitive skills such as empathy, social learning, and potentially theory of mind. These behaviors, often thought to be uniquely human, suggest that the last common ancestor may have had a complex social life, with at least the capacity for sophisticated cognitive functions. Human evolution since the missing link is a story woven with countless threads of diversity, adaptation, and complexity. In this evolutionary mosaic, there's no one-size-fits-all missing link, but rather an array of hominin fossils that contribute to our understanding of our shared ancestry with our chimpanzee relatives. It is not a simple linear progression, tree-dwelling to bipedal, primitive to cognitively complex. It is a richly interconnected web that defies easy categorization. And so, what if there isn't just one piece of the puzzle? What if there are many unique pieces, each revealing different aspects of the final picture? Vertebrates like Tiktaalik evolved in the sea and eventually moved onto land. But fast forward about 350 million years, and the ancestors of whales turned back. For decades, the strange body plan of cetaceans, whales, dolphins, and porpoises had perplexed paleontologists. Some speculated that they might have arisen from marine reptiles. Others suggested that they were ancestors of seals, marsupials like kangaroos, and even a now extinct group of wolf-like carnivores. However, in the late 1990s, genetic data revealed that whales are in fact part of the same evolutionary line that spawned cows, pigs, and camels, a branch called Artiodactyla. Discoveries of fossils from India and Pakistan subsequently fleshed out their family tree, identifying the closest ancient relatives of cetaceans as small, wading, deer-like creatures. These creatures had adapted to their new marine surroundings and given rise to a diverse suite of animals vastly different from their land-dwelling kin. To survive in the sea, as well as modify their body plans, cetaceans had to make internal adaptations, altering their blood, saliva, lungs, and skin. Many of those changes aren't as obvious in fossils, and cetaceans aren't easily studied in the lab. Once again, it was genetics that brought these changes to light. And so, in reality, the story of our evolutionary journey is far from simplistic. It's a complex and intricate process that involves multiple branches, intersections, and convergent paths. There is no single missing link, but rather a vast and interconnected tree of life, with multiple key points of divergence and adaptation. But genetics can only tell you so much, particularly in species as genetically similar as chimpanzees and humans. And so in paleoanthropology, reconstructions of evolutionary relationships have to rely primarily on fossils. Yet it is also difficult to determine from fossils what traits in hominins are primitive, inherited from a distinct ancestral species, and those that are derived and have appeared in the most recent ancestor. This is because we cannot be sure how fossils are related to each other. Indeed, what can sometimes make the search for common ancestors even more difficult is the phenomenon of reverse evolution, where a previously evolved trait reverts back to its ancestral state. another vivid reminder of the intricate nature of evolutionary processes. We've already considered whale evolution, but there's also the example of reverse evolution in snakes. While these legless creatures might seem like a one-way evolutionary street, some species, like the boa constrictor, have reacquired small, vestigial hind limbs. There is also the problem of homoplasy. This is when traits of similar characteristics and functions emerge in different species that do not share a common ancestor. These characteristics arise via convergent evolution, usually due to adaptation to similar environments. And convergence is common in the animal kingdom. An obvious example of this is the evolution of wings in birds and bats. Despite their vastly different biological backgrounds, both developed wings for flight in response to the shared challenge of taking to the skies. This remarkable convergence highlights the adaptability and creativity of nature, showing that it doesn't always follow a predictable path. And bipedalism itself may be another example of convergence. Analyses on the feet of Australopithecus africanus and Homo habilis have demonstrated that they possess mosaic morphologies of ape-like and human-like traits. But intriguingly, they have different combinations of primitive and derived traits. The recently discovered Homo naledi, another example of a hominin that walked with a unique gait. This could imply, within the foot at least, two distinct paths of adaptation to the requirements of bipedalism. These two species might have developed various forms of bipedalism through potentially multiple evolutionary routes in response to similar environmental conditions. And so, evolution, as we understand it today, is far more intricate and multifaceted than the linear, ladder-like progression traditionally depicted. But if evolution is such a complex process, what does that mean for the quest to find the missing link? The fossil record has provided us with a wealth of information about our ancient ancestors. These discoveries have illuminated the gradual but complex process of human evolution, showcasing our shared lineage with chimpanzees as Darwin once predicted. But it is highly likely that we may never discover a singular missing link that perfectly bridges the gap between humans and chimpanzees. Despite this, the collective evidence from the fossil record continues to enrich our understanding of this enthralling evolutionary journey, offering glimpses into the past and reminding us that the story of our origins is beautifully intricate. The missing link is therefore not a necessary piece of evidence for understanding the process of human evolution. Determining a series of linear links is an oversimplification, a somewhat useful metaphor for what was actually a messy process occurring across huge timescales of millions of years. And so, is the missing link really missing if it can never truly be found? You've been watching The Entire History of Humankind. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.